Alright guys, today we're going to talk about logistic growth. Logistic growth. In the last lesson we talked about exponential growth, so today we're going to talk about logistic growth. So let's just first start out with what is the idea of logistic growth. Well, essentially the idea is that in certain situations you want to use an exponential function to model growth. So for instance, let's say you put a little bit of bacteria in a petri dish and it doubles every hour. Well, it's just going to continue to double and double and double, and it's never going to stop. All right. But for a lot of instances, we want to have something that grows quickly at first, but then eventually levels out. So an example of this would be, let's say, human growth. Okay, we don't grow forever. Or plant growth, or perhaps the number of bears in a park because of limited resources. So you can't have an infinite number of bears in a park, even though you may throw a few of them in there at the beginning. They will procreate, and you'll have more and more, but you have limited resources. So for these type of situations, we're going to use a logistic growth model. Now, the differential equation for the logistic growth is right here. dP over dt is equal to Kp m minus p. Now m, pay attention to m. M is the maximum amount of growth. That would be the highest number of bears you could put in a park, or the highest number of fish in a lake, or something like that. That is your carrying capacity. That is your max. That is your, if you want to call it, your upper asymptote, your upper horizontal asymptote. That's where it's going to cap out at, right there. All right. Now, the letter A right here, you are going to be able to determine that from an initial condition, which we'll talk about in the first problem, and K as well is going to be a constant. Now, let me say this. Even though you have the tools to be able to solve this differential equation and get it to here, essentially it's a partial fraction decomposition. Okay, and if you would like more of an explanation on how to do that, you can look at the notes for 366 and 367. All right, the notes will give you a detailed explanation. But essentially, just in case you're curious, you would separate the variables, and you would have, let's see, you would have 1 over p m minus p dp equals k times dt. And so we've separated the variables. We got all the p's on the left and all the t's, if you will, on the right. And you can see that this is going to be a partial fraction decomposition. So it's going to be a over that plus b over that, and that's the idea. But we're not going to get into that. On the AP exam, you will never be required to solve this differential equation. You will be able to assume, anytime it says logistic growth, you will be able to assume this solution right here. And that's what we will use, that and this, in the next problem. All right, let's look at example 1. It says the population of fish in a lake satisfies the logistic differential equation 3p minus p squared over 6,000, where t is measured in years and they give you an initial condition. That's important. So they're telling you when time is equal to 0, there are 4,000 fish. All right, so there are 4,000 fish in the lake. All right, so it's asking in letter A to find the limit as t approaches infinity. In other words, what is the maximum value, right? As time approaches infinity, what is the limit of the number of fish that you can have in this lake? So for that, we need to find capital M. We need to find capital M, which is right there. So for that, here's the trick with these, okay? Here's the trick. what you have to do is you have to take this differential equation and you've got to manipulate it to look like that one. In other words, notice that the P right here that I'm circling cannot have a number underneath it. It has to be simply a P. It cannot be P squared. It can't be P squared over 6,000. It can't be P over anything. It has to be simply P. So what we need to do is we need to factor out a P over 6,000 here. So let's see if this makes sense to you. So we're going to rewrite this as dP over dt equals, we're going to factor out a 1 over 6,000 P. Now, we got to do a little bit of math here. Notice I'm going to circle it. Notice the 3P right there. Well, you have to think to yourself, okay, what do I need to put so that when I distribute this that I pulled out back in, I get 3P? Well, that's just going to be 18,000, okay? 18,000 minus P. All right, now if you're not sure about that, take some time to convince yourself that what I just wrote is the same as the problem that they gave you. If you distribute the 1 over 6,000 P, you get 18,000 divided by 6,000, which is 3P. And then you take this again and distribute it to there, you will get P squared over 6,000. All right, so this, what I'm circling, is your K, which you're going to need later. And this that I'm circling is your M. All right, and let me just draw an arrow right up there. That is your M. That's your maximum. So that is the answer to letter A, right? Letter A, the maximum number of fish is going to be 18,000 fish. Okay? Now also in that problem, it's asking you for the range. It's asking you for what is the range. Now, just to let you know, we know that these logistic functions look like this. Okay? We learned that in pre-cal. It's called the S-curve. All right? Now, you may be thinking, oh, well, the range is just 0 to 18,000. But you have to remember that these are real-life situations. Think about it. If you put 0 fish in a lake, there's no fish there to procreate. It will never get to 18,000. So you have to know that this, we're just going to cross that out. Okay? There is an initial condition that as soon as the lake opens up, they are throwing 4,000 fish in there, and the fish just start procreating, and then it gets to 18,000. So you have to think that's the real life situation going on here. So the range is going to be 4,000 fish to 18,000, and we'll put a parenthesis on that because technically it will never reach 18,000 because this is an upper horizontal asymptote. Okay? And so that is the answer for A and B. And letter C, it's asking us now to write the equation for P of T. Well, it says up here in our little notes that P of T is equal to M, which we now know is 18,000. So I'm going to put that in the place for M. And then it says 1 plus A, which we're going to use our initial condition to get A, all right, E. And then, if you can read it, it says negative parentheses M, which is 18,000, K, which, notice I circled the K earlier, right here. K is going to be 1 over 6,000. So you can just see that's going to be 3, all right? And then parentheses T. All right, so what do we have so far? We have P of T, let me rewrite it, is equal to 18,000 over 1 plus A E to the negative 3T. All right, that's what we have. Now we got to use our initial condition. So it says that when time is 0, the number of fish are 4,000. So 4,000 is going to go over here on the left, and then we have 18,000 over 1 plus. Now, remember, when time is 0, you're going to have e to the 0, which is simply 1. So that's just going to give you a. And then I'm going to multiply both sides by 1 plus a. And that's going to, we multiply this side by 1 plus a. And of course, we know that's going to cancel. And so you're going to distribute this 4,000 in there. And then you're going to have 4,000 plus 4,000a equals 18,000. Now, when you solve that for a, you're going to end up getting 3.5. Okay, that is your a. So we can go back and plug in our final answer for p of t is going to be 18,000 over 1 plus 3.5 e to the negative 3t. And that is your answer for part C. Alright guys, we're going to look at part C, D, and E on this slide here. And part C is saying, for what values of P is the solution curve increasing and when is it decreasing? Justify your answer. Now, let's just think about this thing logically here for a second, okay? We already know, at least I already know, what the graph of this thing looks like, okay? It's a logistic function. This is from pre-cal. So if it's a logistic function, we know that it's going to have a lower asymptote, it's going to have an upper asymptote, and it's going to make the S-curve. Well, we know that it's going to grow from 4,000 to 18,000. So guess what? We already know the answer. What values of the population is it going to be increasing? Well, it's going to be increasing from when the population is 4,000 to when the population is 18,000, right? That's pretty much, the graph tells us that. But we have to justify it. We can't use a graph. We have to use calculus, all right? Not pre-calculus. So, what do we know from previous classes? A function is increasing when what? When its first derivative is positive, okay? So, we have already been given the first derivative. We don't have to take the derivative. We've been given dp dt. That is the derivative, all right? And we got it to be 1 over 6,000 p, and then 18,000 minus p. All right, now, how do we get critical points? We get critical points by setting the derivative equal to 0. All right, so when we set the derivative equal to 0, we get 2 critical points. We get, well, let's just do it. 1 over 6,000 p equals 0. That's the first factor. And then you're going to set 18,000 minus p equal to 0. And you get 2 critical points. P equals 0 and p equals 18,000. Okay, so p equals 0, throw that out there. Population of fish is never going to be 0 because why? It starts at 4,000, right? That's the initial number of fish. So we're going to make a number line. We're going to put 18,000 on our number line. And we might as well put 4,000 on our number line because that's where it starts. So we've got to plug values in that range into the first derivative and prove that the first derivative is positive. And if the first derivative is positive, that means that the solution curve is increasing. Let's try it. Let's plug in 10,000. Okay, so we're going to plug 10,000, which is somewhere around there. We're going to plug that into our differential equation. And you can see, we're going to plug it into here also. You can see you're going to get a positive number times another positive number. Well, hey, that means that the first derivative is positive from 4,000 to 18,000. All right? So that is the answer to letter D. Now, when is it decreasing? It's never decreasing. All right? Because you can see that it's going to be increasing from when it starts, the lowest number of fish, to the highest number of fish. And we have justified our answer there. All right. Now, letter D. For what values of p is the solution curve concave up or concave down? Okay, now what derivative do we get concavity from? The second derivative. So we need to take the second derivative. Now, I'm going to do something here. I would not use this equation here to take the derivative of, because you're going to have to use the product rule. So what I would do is I would go back to the problem that they gave, and notice that it says dp dt is equal to 3p minus p squared over 6,000. Okay, I'm going to take the derivative of that, and so okay, this is the second derivative notation, and I'm going to take the derivative with respect to p. The derivative here is, well, a simple mistake that can easily be made here is to simply just take the derivative like you would normally. So 3p, actually no, 3, all right, 3, and this is wrong, so I'm just trying to show you what you don't want to do. It's easy to say, well, the derivative is just going to be 3 minus p over 3,000, all right? And that is wrong, because you have to remember that we are taking the derivative implicitly with respect to time, right? dp dt, there it is. So you have to do this implicit differentiation. So I'm going to erase this and take the derivative implicitly. So that's going to be 3p prime minus 2 over 6,000p, and then p prime. So it's going to be basically p times, or p over 3,000 times p prime, all right, or dp dt. All right, so now I'm going to factor out a p prime here, and this is going to come in handy for example 3. You'll see why we're doing this. I'm factoring out a p prime, and now we have this as our second derivative. Okay, so now if we set this equal to 0, we get an inflection point, not a critical point, but we get an inflection point if we set this factor equal to 0. We get an inflection point of p equals 9,000. All right, so p equals 9,000. So that is the only inflection point. So now we're going to make a new number line, and on this number line we are going to put 4,000, so we'll say 4k. We'll put the inflection point 9k, and we'll put our maximum value 18k, and we're going to plug numbers into our second derivative. All right, so let's say we plug in 6k. Okay, now this is important, very, 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 very important right here. All right, you have to pay attention to the value of the first derivative at these numbers that you're plugging in. That's going to come back in example 3. So when you plug in 6k into the, okay, let me just write here, 6k. When you plug that into the first derivative, which would really be over here, what kind of number do you get? You get a positive number. So what do we have so far? A positive number, and then when you plug in 6,000 into this p right there, you get 6,000 over 3,000, which is 2. 3 minus 2 is 1. That's a positive number, so what do you get? A positive times a positive, that is a positive. So the graph is concave up from 4,000 to 9,000. All right, well, that makes sense. Look at the graph. It's going to be pretty much concave up, all right, until 9k. And then if you plug in, let's say 12,000 into the first derivative, so why don't we put 12k right here. We plug that into the first derivative. We still get a positive first derivative. So we still have a positive first derivative times 12,000 over 3,000 is 4. 3 minus 4 is negative 1. So that's a negative number. Positive times a negative is a negative. So therefore, it is concave down from 9,000 to 18,000 population. So you can see right there on the graph that it is concave down. All right? And those are the answers for part D. We've justified it. Now, letter E, does the solution have an inflection point? Yes, it does. Okay, right there. And it would be at when the population is 9,000. How do we know? Because the concavity changed from concave up to concave down. It changed from a positive concavity to a negative concavity, so that means there must have been an inflection point there. All right, example 2. This is going to go a lot faster because, hey, notice that the differential equation they gave us for example 2 is exactly the same as the differential equation in example 1. What is the difference? The difference is the initial condition is different. Now, at time 0, there are 10,000 fish, not 4,000. So, remember that in example 1, we had already solved this, so dp dt, we already got to be 1 over 6,000 p, and then 18,000 minus p. So the answer to part A is the same. The limit as t approaches infinity, in other words, the maximum number of fish, well, that's just going to be your m value right there, so that's going to be 18,000. Part A is done. Part B, what is the range of the solution curve? Well, I think you can figure that out. Range is the lowest to highest value. So the lowest number of fish that this particular lake will ever have is 10,000, and it will go to 18,000 once again. So 10,000 to 18,000. That is the number of fish. Okay. For what values of P is the solution curve increasing? Once again, we have already done the work for example 1, so I'm just going to now put on the number line the critical point that we found in example 1, which was 18,000. So I'm going to put that right there. We'll call that 18K. Now, the only difference is that instead of putting 4,000, we're going to put 10,000 here. All right, because that is the initial number of fish in this particular example. And all we're going to do is we're going to plug in a number. Let's just say 14,000. That's right in the middle. We'll plug that in to our differential equation to check the slope or the derivative to see whether it's increasing or decreasing. And we see that it is increasing because 18,000 minus 14,000 is a positive number times another positive number for P. That gives us a positive. So we know that it is going to be increasing from 10K to 18K. When is it decreasing? Well, it's never decreasing. All right. For what values of P is the solution curve concave up? All right. Well, do you guys remember the last one that we just did? The inflection point was 9,000. Okay, let's draw that again. The inflection point was 9,000. And what did we learn in the last example? All right, we learned that between 9,000 and 18,000, the graph was concave down, right? It was concave down. Well, guess what? Our problem here starts at 10,000. So you can't use any of that stuff back there because there's not less than 10,000 fish. So therefore, it will be concave down from 10K, okay, to 18K. Concave down. When will it be concave up? Never, okay, because the only inflection point happened at 9,000. So that's not going to, it's not going to be concave up at that at all. Does it have an inflection point? No, this particular solution does not have an inflection point because 9,000 is outside of the starting and ending value. Part F says sketch the graph. So this is going to be Well, it's going to be an initial condition of 10,000 when time is 0. So that's 10K. And we know that it can only go up to 18,000. So that's going to be our asymptote. And if we were going to draw technically this S-curve, it would look something like this. However, at this point, I'm going to draw the real curve there. So what I just drew in blue is really the solution curve. The other dotted white is just simply the S-curve if we were just sketching the graph. But that would be the solution curve. All right, we're back. Once again, example 3. This should be getting quite boring to you because notice we have our friend again, this same differential equation that we had in examples 1 and example 2. What is the only difference here? The initial condition is that at time 0 there is 20,000 fish in the lake. Oh, so what does that mean? Well, we already established in the first example that the maximum number of fish that we could possibly have is 18,000. Let me write that down again. dP dt is equal to 1 over 6,000 P, 18,000 minus P. All right, and remember, this is our maximum value. And so the lake can't hold any more than 18,000 fish. That's it. That's the maximum. That's the carrying capacity. So they put too many fish in the lake, so the number of fish are going to die because there are insufficient resources to handle that many fish. So we already know, really, if we wanted to sketch this thing, well, it would be, well, let's just say that's 18K, and this is 20K, and this is our horizontal asymptote, and this is our starting value or our initial value. Well, we already know that this guy is going to just decrease, and it's going to approach the 18,000. But we're going to get to that later. All right, so letter A. What is the maximum number of fish, or the limit as time approaches infinity? That's just going to be 18,000. So 18K. All right, letter B. What is the range of the solution curve? Well, range is lowest to highest value. The lowest value is 18,000. However, it's an asymptote. So is it going to really touch 18,000? No, it's going to approach 18,000. So we need to have a parenthesis on 18K, and 20,000, yes, it does actually touch that because that's what it starts with. So that's the answer to letter B. Letter C, for what values of P is the solution curve increasing? Well, once again, we want to make a number line, and on this number line, we are going to put our maximum value, so we'll put 18K, and we'll put our starting value, put 20K right there. And we're going to plug in, let's say 19K. We're going to plug it into our first derivative. Why? Because it's asking about increasing and decreasing. So when the slope is positive, a function is increasing. When the slope is negative, the function is decreasing. This is our slope. They already gave it to us. So we're going to plug 19,000 in there. When we get 18,000 minus 19,000, that gives us a negative 1,000 times a positive number. So what do we get? We get a positive times a negative. That is a negative number. So in this range, it's going to be decreasing. Duh, the picture already tells us that right here has to be decreasing. When is it increasing? It's never increasing, okay? So we can see that. Now, for part D, got to be careful here. Do you guys remember that when we took the, and it's like in the second or third slide, I believe it's the third slide, we took the second derivative and we got, let's see, we got d2p and dt. We got the second derivative. Do you remember that we factored out a p prime? If you don't remember that, you need to go back and look at that. We factored out a p prime, and we got a 3 minus p over 3,000. If you don't do that, then you're going to get the wrong answer. So we're going to plug 19,000, all right, into our second derivative to test the concavity. Oh, but we got to remember that we have to figure out what is the value of the first derivative when the population is 19,000. Oh, okay, that was negative. We just figured that out. So we have a negative number times, okay, well, what is, let me just put this here, 3 minus 19k over 3k. Well, it's going to be around 6, right? 19 over 3 is a little bit more than 6. So 3 minus, or something around 6, is a negative number times the negative first derivative gives us a positive number, and that means that the graph is concave up. Concave up. Well, we knew that. Look at the graph. It's concave up right there, okay? But we have to prove it using calculus. So it's concave up between 18,000 and 20,000. Concave down? Never. Does it have an inflection point? No. Only at 9,000 does it have an inflection point. All right, this is the last example. We're going to go through this pretty quickly here. We see that in part it's actually giving us a differential equation for the logistic function, and it's telling us that it's already solved in the way that we want. Notice that the p is not divided by anything. It's not squared. It's already been factored out. So therefore, we can go ahead and get going here. It says in part A, they want us to, now this is a calculator problem, they want us to write the population as a function of t given the initial condition, 0, 50. Well, if you remember from the very first example, this is the formula for population at any time. The maximum value, remember, is 3,000 here. That's going to be that guy right there. So we can go ahead and plug that into our formula. So part A, it's going to be P of t is going to be 3,000 divided by 1 plus A, which we will use our initial condition to get A in a moment, e to the negative m, which is 3,000, and k, if you remember, k is the number in front of the p, so that's going to be 0.001, and all of that is in parentheses, times t. So that's just going to be negative 3t again over there, so we'll just say 3,000 over 1 plus a e to the negative 3t, and that's equal to the p of t. And so now we're going to plug in our initial condition of 0, 50. So when time is 0, e to the 0 is 1, so we're going to get that same situation we had earlier. So we're going to have 3,000 over 1 plus a equals 50. And multiply both sides by 1 plus a. So that's going to give us 3,000 equals 50 plus 50a. And that's going to give us 2950 equals 50a. Then we divide by 50, and a is going to be 59. So, what is our population? Population at any time t is going to be our maximum value, 3,000, over 1 plus 59 e to the negative 3t. That's the answer for part A. Now, where does your calculator come into play? Well, it comes into play in part B. Now you have to use your solution to A and your graphing calculator to find the size of the population when time is 2. So we are looking for P of 2. So you got to plug 2 in to your population equation, and this is simple math here. Just you need to go ahead and plug that in, and you will get 2617 point something, but you can't have part, so therefore you just round that to 2617. All right. Now part C, use your solution to part A in your graphing calculator to find the number of days that have passed when 2,400 people have contracted the flu. All right. So now it's the idea of plugging in 2,400 into your population and equaling 3,000. Please don't try to solve this by hand. It's not worth it. All right. You're going to use your solver on your TI Inspire calculator, or if you have an 84, you can find the intersection between those two curves. You will get a time value of approximately 1.82 days. All right, and then the last problem is part D. Approximately when will it reach its maximum population? All right, if you use your calculator and you trace and use a trace step of about 0.1, just trace the graph, or you can use the table, and you will see that it takes approximately about 3.4 days in order to reach its maximum value. All right, and once again, you can either use the table or the tracing feature for that. Okay, we are going to practice all of this in class on Tuesday.